Good morning, dear students. So in the last class, we were discussing BPT, right? So we have completed the four complexes. So did you go through the complexes? Yes, hybridization, BPT, four complexes. Out of that, two are of coordination number 6 and two complexes of are coordination number 4. Okay, so these are very important 3-mark question, compulsory question. So did you practice those complexes? Yes. So please go through the complexes. So you need to write the hybridization. So what all things I've mentioned in the last class. Okay, so you have to write stepwise the hybridization, how the central metal atoms ground state. Then after losing the, so you should find out the, suppose, okay, NH3 6 3 plus. So your first step is what? You have to write the electronic configuration of cobalt. Okay. Then second step is find the oxidation state of cobalt. So after, so how, what is the oxidation state? It is cobalt plus 3. Plus 3 means what? It has lost 3 electrons. So cobalt in plus 3 state, it will be 3d7. Sorry, 3d6. Okay, because from 4s to 2 electrons are gone and from 3d7, 1 electron is gone. So it will be 3d6. Okay, argon 18, 3d6. So then you have to write the ground state hybridization. Okay, then cobalt. Okay, so when it comes in contact with NH3, as we know, NH3 is a strong field ligand. So what will happen? Pairing will takes place because the distance between the T2G, okay, T2G and EG orbitals is what? It is more. Okay, so the distance between the T2G and EG is more. So this T2G, what is EG? So that we are going to discuss in CFT. Okay, so don't get confused. So that I'll tell you in CFT. Just remember that whenever you have a strong field ligands like NH3, okay, and we have discussed about cyanide. So that time what will happen? Because the distance between the T2G and EG is more, what will happen? The electron pairing takes place at ground level only. Okay, so now there are 6 electrons. So at the ground, here only at T2G level only, all the electrons are getting paired. Suppose if there were 3d7 electrons. So after the pairing get over at bottom, okay, at T2G, then the next electron can go for EG. Okay, so this is the point. So whenever you have a strong field ligand, what will happen? Whenever you have a strong field ligand, what will happen? The electron pairing will takes place in T2G. Okay, first T2G and then the next electron. Suppose, okay, 3d7 electrons are there. So what will happen after the splitting takes place like this? Okay, so suppose there are 3d7 electrons. So because of the, under the influence of the strong field ligand like your ammonia, so first the electrons, what will happen? So they will get here. So 6 electrons. Now seventh electron, it should go at the top only. Okay, so this is in case of strong field ligand. Now whenever you have a weak field ligand, what will happen to weak field ligand? Weak field ligand like fluorine, fluoride ion. Okay, so that time what will happen? So the distance between the T2G and EG will be less. The distance between the T2G and EG is less. So what will happen? So if there are 3d7 electron again, so 1, 2, 3, 4, 5, 6, 7. Okay, so like this, the electron pairing takes place. So electron pairing does not take place. Okay, so whenever you have a weak field ligand, because the distance between the T2G and EG orbitals are is less. So remember this, okay? So strong field electron pairing takes place under the influence of strong ligands, and whenever you have a weak ligands, then electron pairing does not take place. Okay, fine. So today, so after that, what was the next step? So then we make availability of the ligand orbitals. So after the ligand orbitals, so the how, so there were NH3 6 cobalt 3 plus, right? So what will happen? So 1 2 3 4 5, so and 4p orbitals. So this is 3d 4s and 4p. So 6 electrons. So electron pairing takes place, and we make how many? 6 ligand orbitals vacant. So 1 2 3 4 5 and 6. So what is the hybridization shown by this complex is D2sp3, because we are making use of two orbitals of D. So it is D2, S is 1, so S, and P is 3. So it is sp3. Okay. So D2sp3 hybridization. And we are making use of inner orbitals, right? So it is an inner orbital complex. It is an inner orbital complex, or it is called as what? Inner orbital complex, or it is called as low spin. Okay, it is called as low spin complex. Okay, it is called as inner orbital complex, or it is called as the low spin complex. Fine, then we discuss about what the properties. Magnetic properties is what? Magnetic property, because all the electrons are paired here, so it is diamagnetic in nature. Okay, if there is one also unpaired electron, then it gives rise to what? It gives rise to paramagnetic behavior of the complex. So this is diamagnetic. Then when we talk about the geometry, okay, when we talk about geometry, so the cobalt is in center, and because it is a central metal ion, and there are six ligands. Okay, whenever you have a coordination number six, that is when you have around the central metal atom. So if there are six ligands, okay, then it gives rise to what type of geometry? It gives rise to octahedral geometry. Okay, it gives rise to octahedral geometry. So like this is the octahedral geometry. Okay. So this is the octahedral geometry, like this. Okay. So cobalt in the center, NH3, 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 NH3. Okay. Then so this is a square planar. So at the four corner, you have four this. Okay. Now this so four ligands at the four corners, four ligands at the four corners of the square planar, and two are above and below the square planar. Okay, now how this see here? So this is your octahedral geometry. Got it now? Now you can see it clearly. Okay, so this is a octahedral geometry. Octahedral. So whenever you have uh, six coordination number, it will show octahedral geometry. And what is the hybridization? D2sp3. Is it clear? So please study all these four hybridization, okay, or four complexes. Very important. Okay, so then we are discussing about the drawbacks or the limitation. So next, now we are going to start with the next theory. So which explains the bonding, that is the bonding between the metal and ligand. So the next is CFT, okay, because it could not, why we went for the next theory? Because VBT could not explain, okay, it could not explain the magnetic data. Okay, it could not explain the color for the coordination compounds. It could not distinguish between the strong field ligands and the weak field ligands. Okay, and it could not explain if the coordination number is 4, why it is showing square planar itself. Okay, it can show tetrahedral, also, but it could not explain that also accurately. So because it failed, that is CFT. Okay, so this crystal field theory, CFC is what? CFT, crystal field theory. So this was proposed by whom? This was proposed by Hans Bethe, okay, and Van Wilk. So these were the scientists who proposed the crystal fields theory. Then what does crystal field theory tells you? It tells you the interaction, okay, the interaction between the metal and the ligand. It tells you the interaction between the metal and the ligand. In VBT, okay, so in VBT also it could tell the interaction between the metal and ligand, but what was assumed that the metal and ligand, it is a covalent coordinate bond, okay, where we had discussed this in the VBT. So what does the scientist Pauling he told in PPT that metal ligand interaction is purely a covalent coordinate bond. But in CFT, okay, what does the scientist told that the interaction between the metal and ligand is purely electrostatic. Okay, it is purely electrostatic. So one is giving electrons, another is taking electrons. Okay, electrostatic attraction is what? One is giving, another is taking, like that. So it is a electrostatic attraction. So in CFT, what does the scientist assume? That the interaction between the metal and ligand is purely electrostatic. In VBT, what was explained? That the metal ligand interaction is a purely a covalent coordinate bond. Okay. So let us discuss the uh, points. So this was the whatever the bond is formed. Okay, whatever the bond is formed between the metal and ligand is purely electrostatic. Okay, it is purely electrostatic. Electrostatic means what? Ionic bond. Okay, ionic bond. So I said what? One is taking electrons. Okay, so this ligand is giving electrons and this is taking electrons, right? So this is giving, this is taking. So it is what? A purely a electrostatic uh, bond or ionic bond. So the bond which is formed between the metal and ligand is purely ionic. Okay. And the second point is what? This ligands, whatever the ligands are there. Now around the central metal atom, so we assume that the metal is represented as M. Okay, and around this metal, whatever the ligands are there, okay, whatever the ligands are there, these ligands are treated as point charges. Okay, they are treated as what? They are treated as point charges. So please make notes of this. So you can write the short forms, okay, short notes of the theory. So what is the second theory? What is the second point in this theory according to CFT? So what does the scientist said that the ligands? So these ligands, these are the point charges. They are treated as the point charges. Okay. So either they are the anions, okay, they are the anions or neutral molecules, okay. Which are the anions? Anions like Cl minus, Br minus, F minus, Cn minus, okay. So these are the anions. Neutral molecules like your NH3, H2, okay. So these ligands are treated as what? They are treated as the point charges, okay. So they are treated as a dipoles. Okay, they are treated as a dipoles. Now, so whenever you have a metal, okay, so third point, so this is the third point, that whenever you have a isolated metal ion, okay, whenever you have a isolated metal ion, these metal ions will have 5 orbitals. Okay, 1, 2, 3, 4, 5. So these are going to have 5d orbitals, right? We have seen now. Right, we have seen 4 complexes previously. So there you have seen that there are d orbitals. Okay, you know that s orbital consists of 1, p consists of 3 orbitals, and d consists of 5. Okay, and your f consists of 7. 3, 4, 5, 6, 7. Okay, now s, maximum number of electrons accommodated is s is 2. Right, maximum number of electrons accommodated in S is 2. In P, the maximum number of electrons can accommodate is 6. Right, we know this. Then the maximum number of electrons accommodated in d orbitals is 10. Okay, then maximum number of electrons accommodated in your f orbitals is 14, right? 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. So, how many electrons can accommodate? 14. So, 14, 10 to maximum. Okay, I'm talking about maximum number. So now, so whenever you have, when we are talking about your uh, coordination compounds, okay, we are going to uh, deal with respect to d orbitals. Okay, we are interested in d orbitals. Now here, so whenever, so what is the third point? That is whenever you have a isolated metal ion. So this isolated metal ion is having 5d orbital. Okay. These are having what? These are having 5d orbitals, and these 5d orbitals are degenerate. Now, what do you mean by the word degenerate? Degenerate means they are having equal energy. All these orbitals are of equal energy when in case of a isolated ion. Okay. When you have a isolated ion. So whenever you have a isolated ion, so they are having what? They are having a 5d orbitals, and these 5d orbitals are what? These are degenerate. That is, they are having equal energy, or you can say same energy. Okay, you can say same energy. So degenerate means all the orbitals are they are having a same energy. Okay, so when we, what do you mean by isolated? When it does not comes in contact with ligand. Okay, so till then it will be isolated. Now suppose cobalt plus 3, nickel plus 2. These are your isolated ion. Now it's 3 minus. Now this is what? This is not a isolated ion. So whenever you have like this isolated ion, so the whatever the d orbitals are there, these are degenerate. Okay, they are having 5d orbitals, and these are degenerate. Okay, so these degeneracy is maintained when the metal ion is surrounded by a spherical field of negative charge of ligands. Now, under the influence of the ligands, what will happen? Under the influence of the ligand, okay, so the energy is not similar. Okay, so when, so suppose the metal is there, okay, the metal is there, so free metal is there, free metal ion. This free metal ion, what I said, that the orbitals are, so suppose I am what I'm doing, I'm representing them in like this. Okay, I'm representing each orbital like this. Can you tell me the 5d orbitals? So I said that there are 5d orbitals. Okay, 1, 2, 3, 4, 5. So these are the d orbitals. Can you name this? Yes. So s orbital is spherical in shape. Okay, so it is only yes. When we talk about p orbital, so these are what shape? What is the shape? Yes, what is the shape of p orbitals? Can anyone tell me? Last year you have discussed, first year. Do you know what is the shape of p orbitals? S orbital is represented as spherical shape. Okay. What is the shape of p orbitals? Anybody? Yes, anybody? So it is dumbbell shape, right? It is dumbbell shape. So the p orbitals is dumbbell shape. Yes, Sri Varuni has answered. Very good. And what about d orbitals? D orbitals. So these are what? This is p y. Okay, p x y. You can take, or you can just represent. So this is on y axis. Okay. So and this is py, px, and this is pz. Okay. So these are the, so these are the orbitals. So px, py, and pz. So these are the p orbitals. And what about this is double dumbbell? Yes, very good. So d orbital is double dumbbell. So how is it represented? So d xy, d yz, d xz, then d x square minus y square, and d z square. So these are the 5 orbitals. Okay. So I'll write it correctly. So it is d xy, dyz, dxz, dx square minus y square, and dz square. Okay, so these are the five orbitals. So we represent each this. Okay, so these are named like this. So dxy, dyz, dxz, dx square minus y square, and dz square. Fine. Okay. So these are the five d orbitals. So until and unless it is free metal ion, they are all having same energy. Okay, they are having all same energy. So it is represented like this. Now, when it comes in contact with what? When it comes in contact with the ligands. Okay, when it comes in contact with the ligand, what will happen? The ligands are negative charge. They are represented as points. So okay, it is the energy is, so 1, 2, 3, 4, 5. The energy is raised. Okay. So average energy of d orbital in a spherical field. So the energy is raised. Okay. The energy is raised. So this is when it comes in metal ion. Now when the spherical field ligand, okay, when it is surrounded by the ligand, what will happen? The splitting takes place. Okay. Then the splitting takes place. How the splitting takes place? It splits up into, suppose 1, 2, 3, 4, 5. So this is a free metal ion. So free metal ion. Okay. Now what is happening when it comes in contact with a spherical field? Okay. So this is the spherical field when it comes in contact with the. So the energy is raised. Now when it comes in contact with the d orbitals. Okay. That is when it comes in contact with the ligand. The orbitals are split. How they are splitted? They are splitted into T2G and EG. Okay. T2G consists of what? It consists of, so what are the orbitals? DXY, DYZ, DXZ, dx square minus y square, and dz square. So when it comes in contact with the ligands, what will happen? The energy is splitted. Hmm. So it is splitted into T2G orbitals and EG orbitals. Now T2G consists of dxy, dyz, and dxz. And what is EG? Dx square minus y square and dz square. Okay, remember that. Now, these two orbitals, okay, that is T2G and EG, they are separated by a barycenter. Okay, they are separated by a barycenter of what? Of, it is represented as delta O. And this is the barycenter, means how it is separated. So these both, so the distance between the EG and T2G is delta O. The distance between the EG and T2G is what? It is delta O. And this is your barycenter. Barycenter means how the T2G and EG are separated. Okay. So this is separated with a distance of 2.5 delta O. And this is separated from the barycenter. It is separated by 3.5, 3 by 5 delta O. Okay. So this is the representation. Okay. So this is when you have a, so this, so this splitting, okay. So when the ligand, when it comes in contact, so the complex, the negative field due to the ligand is not symmetric. So when the metal ion is in free state, the d orbitals are in symmetric. Okay, they are symmetric. Okay, they are symmetric. But when it comes in contact with the your ligands, what will happen? It becomes asymmetric and the splitting takes place. Okay, so when it comes in contact with the ligands, the d orbitals are asymmetric, and what will happen? It is not symmetric, and what will happen? The splitting takes place. So splitting of d orbital takes place. So whatever the energy was same, now it is not same. Okay, because when it comes in contact with the ligand, and this splitting of d orbitals, it is called as crystal field splitting. Okay, it is called as crystal field splitting. Now when the crystal field splitting takes place in an octahedral complex, it is represented by delta O, and when it comes in contact with the tetrahedral complexes, then it is represented as delta T. Okay, delta T. So this is about your crystal field splitting. So this is crystal. So here, so these are the double dumbbell shape. Or okay, I have shown you how we represent s orbital. I have shown you how we represent p orbital. So these are the d orbitals. So this is dxy, this is dyz, this is xz, this is dx square minus y square, and this is dz square. Okay, so these are all double dumbbell shape. Okay, these are all double dumbbell shape. So these are the 5d orbitals. So when the metal, okay, central metal ion, these are what? When they are free in the free metal ion state, they are symmetric. Okay, they are symmetric, and you can say they are degenerate. All the orbitals are degenerate, means they are having same energy. But when it comes in contact with the ligands, the degeneracy is lost. Okay, degeneracy is lost. The it is not more symmetric, and what will happen, the crystal field splitting takes place. Okay, okay, fine. So let us discuss about the, so this is, okay, so this is your so this, okay, so CFT. So just now whatever I have told, so just will revise once more. So this is a crystal field splitting, crystal splitting in octahedral, okay, octahedral compounds. So in the place in the octahedral complexes. Octahedral means what? When you have the coordination number 6. Okay, when you have coordination 6. Okay, fine. So in an octahedral complexes, now when metal is there, okay, so okay, metal is in free state. So when the metal is in free state, there is what? All the orbitals are, so you can see all the orbitals are at the same, they are degenerate, means they are having all same energy. So this is when the metal is in free state. Okay, free state. Now, so when we are talking about octahedral, now octahedral means what? Metal is there and it is coming in contact with how many ligands? 6 ligands. Okay, it is coming in contact with the 6 ligands. Now here, these 6 ligands, they are said to be lying on the 3 coordinate axes. Which are the 3 coordinate axes, students? X, Y, and Z. So all these ligands, they are lying in what? They are lying along this 3 coordinate axis. Okay. Now when this ligand is approaching, okay, when the ligand is approaching the central metal ion, what is happening? The d orbitals which are lying along the, okay. Now here when you see, just see the orbitals. Here what you can see, okay, when you are seeing the orbitals, okay, so your dx square minus y square and dz square minus, they are on the axis. Okay, they are on the axis. You can see these and this, it is on the axis. Okay, on the axis. And this is in between the axis. Okay, you can see that this is in between the axis. Here also you can see. Right, this is not on the axis, this is in between the axis. Which are in between the axis? Your dxy, dyz, and dxz. So these are in between the axis, and your dx square minus y square and dz square is on the axis. Okay, remember that. So now when we are discussing about the your this what crystal field theory in the octahedral complex. So here they are degenerate, they are degenerate. Okay. Now when this metal, when it comes in contact with the 6 ligands, so what will happen? What we discussed, that all the 6 ligands, okay, they are approaching, they are coming towards the central metal ion. So whatever, so which are the ligands, which are the d orbitals which are lying on the axis? It is dx square and y square and dz square. Okay, so these are lying on the axis. So this will experience more repulsion. Okay, they will experience more repulsion. You know now what is attraction, what is repulsion. Okay, so because between the if you have negative charge, what will happen? They will not attract, repulsion will be there. Okay, and when you have a positive and negative, then what will happen? attraction takes place. Now here, what is happening? As ligands are also negative charge, okay, and your orbitals, that is dx square minus y square, they are also uh, on the axis. What will happen? Negative, negative, the repulsion starts to takes place when your ligand is approaching the central metal ion. And what will happen? Thus, the energy of the dx square minus y square and dz square will increase. Okay. And okay, so what? So here the repulsion will be more between these orbitals, and your dx square minus this, okay, dx y, dx z and dy square, they will experience less repulsion. So it will occupy the uh, this, okay, and because of the repulsion, they will split and they will occupy the upper level. Okay, so because of this, their energy decreases here, and here their energy increases. Why? Because they are experiencing more repulsion. Okay. So what you need to remember, so when the metal is there in an isolated state, all the energy, all the orbitals are degenerate, means they are having same energy. Now, when the ligand is approaching the central metal ion, when the ligand is approaching the central metal ion, what will happen? The orbitals which are on the axis, the orbitals are which are on the axis, that is dx square minus y square and dz square. Okay, when they come in contact with the ligand, okay, as the ligand is approaching the central metal ion, the orbitals which are along the axis, okay, so what will happen between the ligand and these orbitals? They will experience more repulsion. Okay, because of more repulsion, what will happen? Their energy will increase and they will occupy the upper limit. Okay, they will occupy the upper this, and they will give rise to EG orbitals. Okay, so this set of orbitals are called as the EG orbitals, and this dxy, dxyz, and dxz, this will experience less repulsion. Okay, and what will happen? There will be less energy. Okay, less energy is utilized, and they will split into what? T2G orbitals. Okay, they will split into T2G orbitals. So whatever the degeneracy is there, that is removed. Okay, and this type of twist effect is called as the so this T2G and EG, just now I have told, it is separated by a distance of delta O, or it is repeating when it takes place when a ligand is approaching the central metal ion. Okay, it is splitting into EG and T2G, and this distance is termed as delta O in octahedral complexes. Okay, remember, in octahedral complexes it is given as delta O. Then we have discussed, okay, so between the T2G and EG, there is a Berry center. So this is a Berry center. It is called as a Berry center. And your T2G, okay, and EG is separated by a distance. So this is separated by 3 pi 5 delta O, and this is represented by 2 pi pi delta O. Okay, so this is the splitting in a octahedral. This octahedral splitting takes place. Is it clear? Yes, any doubts up to here? So very important, the crystal field theory. So any one of the crystal field theory will be asked. Either they will ask you to explain the crystal field splitting in octahedral complex or in tetrahedral complex. So important question asked for 3 to 4 marks. Okay. So any one of the crystal field theory will be asked. Any doubts you can ask? Any doubts in this? Okay, fine. So next is your Okay. So next is what? Next is your spectrochemical series. Okay, spectrochemical series. So what is the spectrochemical series? So whatever the crystal field splitting takes place, okay, the crystal field splitting, that is your CFT, okay, it depends on what, how does the crystal field splitting takes place? It depends upon the approach of the ligand, okay. So it depends on what? It depends on two factors. The first is what? Ligands. It depends on the that is the field produced by the ligands, and second is the charge on the metal ion. Charge on metal ion. So crystal field splitting. Okay, crystal field theory. So I'll write it as CFS. Okay, crystal field splitting depends on two factors. The first one is the field which is produced. Okay, field which is produced by the ligands, and second one is the charge on the metal ion. Charge on the metal ion. So these are the two factors. So whenever you have a strong field ligand, okay, whenever you have a strong field ligands, what will happen? Strong field ligands, what it will do? It will cause more splitting. Okay, it will cause more splitting. We have seen this, right? Crystal field theory, whenever you have a this what strong field ligand, that the distance will be more. The distance will be more. And weak field ligand, weak field ligand, okay, less splitting. Less splitting takes place. So how is the less splitting means? I'll represent here only. So less splitting means, okay, so like this. So distance is less. So this is when you have weak field ligand, and this is when you have a strong field ligand. Okay, remember that. So whenever you have a strong field ligand, the splitting will be more. Whenever you have a weak field ligand, splitting will be less. Okay. So these are the two important points which you have to remember. So based upon the experimental observation, what is done of the d orbitals, okay, the ligands, okay, they are arranged. So the ligands are arranged in increasing order. Increasing order. Now you need to know, no, which are the ligands which are causing strong field ligand, which will cause weak field ligand. So what they have done, okay, scientists, what they have done, they have arranged the ligands according to increasing order, okay, of their field strength, okay, of their field strength, okay, field strength, and this is termed as, okay, and this is termed as what? So depending on what they have arrange the ligands in their field strength. This series is called as the spectrochemical series. This is called as what? Spectrochemical series. Okay, remember this. So crystal field theory, it depends on two factors. The first is what? The field which is produced by the ligand. Okay, field produced by ligand. Okay, and the second factor is what? The charge on the central metal ion. Okay, charge on the central metal ion. Then strong field ligands, whenever you have strong field ligand, more splitting takes place. Okay, and weak field ligands, less splitting takes place. So depending upon the so ligands, okay, so on the experimental observation, what is done, the ligands are arranged in the increasing order of their field strength. Okay, and this is termed as spectrochemical series. What it is termed as? Spectrochemical series. So let us see how they are termed. So increasing order means this will be, okay, so it starts with iodide, then you have bromide, then you have SCN minus. So you need to know this. Please note it down, very important. Then you have Cl minus, then you have S2 minus, then you have fluoride ion, then you have hydroxide ion, then you have oxalate ion, then you have water, then you have NCS, that is your isocyanide ion, then you have EDTA, tetra ethylene diamine tetraacetate. Then you have ammonia, NH3. Then you have ethylene diamine. Then it continues up to cyanide and carbonate. Okay. Now here, what are, so these are the weak field ligands. Okay. These are the weak field ligands, and these are the strong field ligands. These are the strong ligands and the intermediate. Okay. Here, these are what? These are your neutral ligands. Okay. These are your neutral ligands, or these also comes under your weak ligands only. Okay. Water, ammonia. Sorry, ammonia is a strong field ligand, right? So yes, your water and all, it is a neutral ligand. Okay. So like this is your crystal, about your spectrochemical series. Okay, any doubts? So ammonia is the strong field. Okay, so this is the spectrochemical series. So what do you mean by spectrochemical series? So when the ligands are arranged in the increasing order of the filter strength, okay, then this series is termed as the spectrochemical series. So depending upon the ligands, the splitting takes place. If it is a strong field ligand, splitting will be more. If it is a weak field ligand, it will be less. Okay. So if it is a strong field ligand, what will happen? The pairing takes place at this, okay, at the bottom only. Okay, first the pairing takes place at bottom, then the remaining electrons will go and pair, they will occupy the upper orbitals. Okay, if the weak field ligand, what will happen? First the orbitals will be filled singly. Okay, 5 orbitals will be filled singly, and then the pairing will takes place. Okay, any doubt up to your? Any doubts? So today we have seen about what is CFT, that is crystal field theory. What are the points? Okay, what does the theory talks about? Then we have discussed about the crystal field splitting in octahedral complexes. Very important. Asked for 3 to 4 marks. Okay, so you have to explain with the splitting pattern. So you have to show the splitting pattern. You have to show what are T2G, what are EG, what is Berry center, okay, how the distance it is discussed about the spectrochemical series. Okay, so the next is crystal fields splitting in tetrahedral complexes. So that we will see in the next class. Okay, so tetrahedral complexes splitting is there. So that we'll discuss in next class. So anyone, but octahedral complex splitting in octahedral complex is very important. Okay, tetrahedral complex is also important, but it is rarely asked. Okay, so but you have study both the splitting patterns because any question can be asked. Okay, is it clear? Is it clear? Okay, so that we'll discuss in tomorrow's class. Fine. Okay then. So I shall end the session here. Okay, we'll meet in tomorrow's class. Thank you.